Okay, so we're in chapter 10 here, second to last chapter, and we were talking about really solutions in this chapter. And the first part was a little bit some new stuff, some old stuff sort of mixed in as we were talking about. We talked about again the idea of sort of solubility in terms of sort of mixing solutions together or other substances together, especially solutions. And remember, really sort of whether or not something is soluble in each other does a lot of times depend on sort of those intermolecular forces that we talked about in the previous chapter. So the overall idea there is, if we're going to sort of mix, say, a couple of solutions together and we want those solutions to mix and be soluble in each other or miscible in each other. If we're talking kind of about two liquids, what we're looking for is really things that share very similar intermolecular forces. If they share very similar intermolecular forces, what that really means is what you're doing is you're basically replacing their kind of interactions with themselves. And that's sort of what we're doing when we're kind of mixing things together is, you got to sort of replace, the reaction of the one substance with itself with the substance and another substance coming in. So if they do share these similar sort of intermolecular forces, when they sort of get together, they're going to have that sort of way of interacting with one another, which they're sort of familiar with, if you want to think about it that way. So if one person uses dipole-dipole interaction, the other one uses dipole-dipole interaction, it's not very hard for them to basically interact with one another and, sort of dissolve or mix and be soluble in one each other. When we get, things that really don't share, for the most part, the same intermolecular forces, then we really start to get trouble. We really start to get a situation where, they're going to sort of try, if you want to think about it that way, kind of try a little bit, but there's really no sort of long way for them to maintain that connection. Pretty much as we talked about with those intermolecular forces, there's really three types of those intermolecular forces. There's dipole-dipole, which is really what we see with polar and polar guys. There's hydrogen bonding, which we also see with polar guys that obviously have the ability to hydrogen bond. And then there's dispersion forces, which is essentially what non-polar guys sort of use as their main and sort of only intermolecular force. And remember, dispersion forces are the weakest. Hydrogen bonding is the strongest out of those three. So that brings up an idea in terms of, as we talked about many times up to this point, of like dissolves like. So when you're trying to predict whether or not two things would be sort of soluble in each other, if they have similar type of intermolecular forces, or they're a similar type of compound, which means maybe they're a polar compound and a polar compound, those guys are going to be fine together. An ionic compound and a polar compound, again, as we talked about, they can use those ion dipole interactions. And then obviously non-polar and non-polar, which is sometimes the one that people sort of mess up on because they have that idea of non-polar not being really able to interact. But non-polar things and non-polar things are very soluble in each other, again, because the major way that they normally sort of interact with themselves is through dispersion forces. So when they come across another non-polar sort of molecule, they're able to interact well with it. Again, it's only when we kind of cross over there and go the non-polar polar route that we do run into trouble. So it's that like dissolves like thing that we talk a lot about. We then sort of talked a little bit about some review of some concentration type units, percent mass, molarity. But there's two sort of concentration units there that we talked about that we will see here going on today, and some other properties that we're going to talk about. And those were molality, which again is different than molarity, molality being the moles of the solute over kilograms of solvent, and also our mole fraction. So those are two things that we will see again here as we kind of finish up this chapter. Any questions on the stuff that we talked about last time? Okay, then we are going to kind of continue on here and talk about properties of solution, which are referred to as colligative properties. Colligative properties, they're really all about really the number of particles that are dissolved in a solution, for example. And what these things affect is they affect things like boiling points, they affect things like freezing points, vapor pressure of a solution, and so forth. So how do these things sort of work? Well, it's sort of a basic idea of, if we think about, say, a freezing situation or something like that. And if we just had, say, a pure solvent by itself, something like water, for example, just a thing of water here, right? And let's say that we wanted to sort of freeze this guy, right? So, or actually freeze or boil this guy. We'll go boiling. Why not? Same thing sort of happens, but let's just kind of draw my water molecules as like circles. I guess we'll do it this way. So let's say we want to go heat this guy up. As we would heat these guys up, at some point, as we talked about, basically our water molecules will gain enough energy and kind of make those bubbles, and those bubbles can basically kind of freely shoot out to the surface and sort of start to boil. In addition, if we were sort of freezing it, for example, again, I'll just draw some water molecules as circles here. As we sort of lower the temperature and start the freezing process, there's really nothing in the way here. So these water molecules can kind of come together a little bit more and make sort of our ice, basically. And by the solvent by itself, there's really nothing to sort of hinder that or get in the way. Now, if we make a solution that includes water as a solvent, and we make like a sodium chloride solution, for example, that basically means that we put some solute that's sodium chloride, and we put some solvent, right, that is water. So essentially here, if we kind of look at the same situation, and I'll draw my water molecules here. I'm going to heat it. The difference, though, between, say, this situation here and this situation here is the guy on the right is not really the pure solvent by itself. It also has some sodium chloride in it, which, as we know, when sodium chloride goes in there, it's going to make some sodium ions, some chloride ions, right? Some sodium ions, some chloride ions. You can even kind of see just from my really bad drawing here, it's getting a little bit crowded in there, right? So what these sort of dissolved solute does in these sort of situations when we talk about sort of colligative properties is, for lack of a better description, they sort of get in the way. So think about now, as we start to heat this water molecule, say here, for example, now it's got to kind of work its way sort of around all this other stuff that's in its way. It's going to need a little bit more energy to kind of break through and to get through everybody, basically to get out of the solution in order to freeze, which is going to require a little bit more energy, which is going to bring our boiling point up, right? More energy means you need more temperature to do that. More temperature means a higher boiling point. And again, it's really the presence of these extra things or particles that are floating around in the solution that really sort of gets in the way of the natural process that would normally happen with a solvent by itself if there really was nothing else dissolved in there. So the idea of the colligative properties is really, when you go and sort of dissolve some stuff in like a solvent such as water, you're basically putting a lot more sort of obstacles in the way. And these things, for the most part, kind of get in the way of sort of that natural process of that solvent, where it would freeze, natural process where it would boil, and so forth. So what would we sort of see in this situation, as we'll talk about here in just a second? We'll basically see that, say water boils at a particular temperature, say 100 degrees. Our solution may boil at like 105 degrees because it needs that a little extra energy to sort of navigate through all the extra particles that are basically dissolved in there. Any questions on that there? So the first thing that it sort of affects, or one thing that it affects, is what is referred to as the vapor pressure. And we talked about sort of the vapor pressure. The vapor pressure is related to, obviously, the gas molecules that are above a liquid, right? And as we talked about, it's sort of the surface of a liquid. You really do have these guys jumping in and out of solution, but you do have a certain amount of vapor or gas molecules, if you will, up there above the liquid. And obviously, the more gas molecules that you have above the surface of the liquid, the greater the vapor pressure, right? Because those gas molecules will be contributing to pressure. So the vapor pressure of the substance depends on the nature of the substance and also its temperature. When we add a solute to a substance, its vapor pressure is lowered. The molecules of the substance cannot evaporate to the surface as rapidly as they normally could in the absence of it. So that's sort of what I was alluding to in my last drawing, same sort of situation. When we sort of dissolve all these things in here, we'll just call them like green circles, something that's dissolved in there. Again, in order for us to get vapor pressure, we need to release those liquid guys to the surface to form gas molecules. And again, you got a lot more stuff in the way when we start to dissolve it. And that will end up lowering the vapor pressure because there will end up being less guys that basically make it to the surface at that point. This is basically displayed by what is referred to as Raoult's law, and that is PZ is equal to XZ, P naught times Z. And the PZ is the vapor pressure of the component. Our X here is our same guy that we've seen a number of times up to this point. This is our mole fraction. So again, a reminder that as we kind of reviewed yesterday as well, that's our mole fraction, which essentially is, again, the moles of what you're interested in divided by the total moles, right? And then our P not Z there is going to be our vapor pressure of our pure substance. Now, the vapor pressure lowering may be defined as the vapor pressure of the pure substance minus the vapor pressure in the solution. So the change in the pressure basically is kind of where our vapor pressure would normally be by the solvent by itself minus where it is sort of in that solution, again, because it's vapor pressure lowering. So we will end up with a lower vapor pressure than what we started with. All right, so why don't we take a look at one here and kind of see what we got going on here. So why don't you take a second here and see what you come up with. The vapor pressure of ethyl alcohol is 66.5. Calculate the vapor pressure of ethyl alcohol in a solution if 0.2 moles of glucose is dissolved in 1.25 moles of the alcohol. So take a moment or two, see what you come up with. Okay, so let's take a look at it. So we are going to obviously deal with vapor pressure, so we'll use Raoult's law there. And again, as we saw on the previous slide, it is our PZ is equal to XZ, P naught. Again, the first P there is pretty much the vapor pressure in the solution. The X is the mole fraction of our component. And then obviously P naught is the sort of vapor pressure of just the solvent by itself. In this case, we're looking at the alcohol. So we would want the mole fraction of the alcohol. So the 1.25 is how many moles of the alcohol there was. We obviously need the total moles, which would be found obviously by adding those two numbers together, the 1.25 moles of the alcohol plus the 0.2 moles of the glucose. Right. And again, that gives us our 1.45 moles, which is our total moles. And that gives us a mole fraction of 0.862, which is this guy. The vapor pressure of the pure solvent there is 66.5. So we can then basically put it into that formula. And what we end up seeing is we end up with a vapor pressure of the solution that is 57.3 torr. 57.3 torr is less than the vapor pressure of the ethyl alcohol by itself. So what we see is the vapor pressure has gone down. First off, any questions on the calculation part here? Now, what does this really mean? Well, what it really means, if we could kind of see if it makes sense to us, is if we have ethyl alcohol by itself, again, nothing else basically dissolved in there. As we talked about, pretty much this guy, if we started to heat it or just naturally, it's got a pretty straight run out there, and it's going to be able to put up a lot more sort of gas molecules above the liquid. Again, the presence of that more gas molecules going to create a larger sort of vapor pressure that's going to occur. Now we take our same guy here and we put in there our glucose, which is basically carbons, hydrogens, and oxygen. So we put a bunch of glucose molecules in there, get it to dissolve. Now, as we try to go through this process, it's going to be a little bit harder. It's going to take a little bit longer, again, for these guys to kind of weave themselves around this stuff, to try to escape sort of the solution. Going to put less gas molecules above the liquid in this case. Again, less gas molecules actually are able to make it there kind of to the surface, going to result in a lower vapor pressure that's happening when we have the glucose dissolved in the ethyl alcohol. Any questions on that there? So again, our answer does really make sense, and that's sense of what's going on. Another important sort of property that's sort of affected by these sort of colligative properties and sort of the presence of these different sort of particles that are dissolved in these solutions is the freezing point. Now, when we talk about freezing point, that obviously is the point where, we sort of lose energy, everybody comes together and to sort of the solid phase. Now, what ends up happening is, again, the addition of those sort of particles that are floating around sort of gets in the way of the natural process of where, say, the solvent by itself, like water, where those water molecules would normally just kind of come together, nothing really in the way. Now, as they try to come together, they got all these particles in the way. They got to kind of move around them and sort of, kind of avoid them, if you will. And the result of that, what we see is actually the freezing point temperature actually starts to be depressed, which basically means that the freezing point temperature actually lowers. So when we talk about something like water, where it normally freezes at 0 degrees Celsius, put something in there like some rock salt or something like that, we will now see that perhaps it goes down and freezes at like -4 degrees Celsius or -5 or -2 degrees Celsius. So we have this freezing point depression where our solution that has the solute sort of dissolved in it will then lower the actual freezing point of that solution. So the addition of that solute to the solvent will cause the freezing point to be lower. Again, as we've been talking about, sort of the particles really, for the most part, get in the way of that sort of really ordered way at which a solid will sort of come together. And we get this equation here, which is the freezing point depression equation. This is the delta T, which is actually the change in freezing point temperature. Kf is a constant. It is the freezing point constant. And M is our molality. So these are some things that we've seen before. So let's talk about a couple of these things, just so we're clear. First off, the molality is our little m, which is our moles per kilogram of solvent. So again, a reminder that it is not molarity, but it is that molality. Kf is actually a freezing point constant. And a freezing point constant is actually a value that you find from a table. Now, it's really important. Sometimes people really struggle with this, actually going to a table and looking up the Kf value, and that's what we'll talk about in just a second, the Kb value and stuff like that. And the reason they struggle is in the problem, they talk about a solution that was made. Maybe it's like a sodium chloride solution, maybe it's some type of solution of that nature. And people go to the table and go, I don't see sodium chloride there at all listed on the table. And the reason for that is the freezing point constant is not about the actual solution that is made, but it is based on the solvent. So the freezing point value that you would find for the table is based on the actual solvent, and that's what you should look for. What that means is, for the most part, if you have some type of ionic compound or something like that, and you see the word kind of aqueous next to it, you can probably safely assume in a lot of cases that the solvent is water. But let me put a little sort of asterisk there next to it. A reminder that, as we talked about previously as well, not every situation calls for water being the solvent, and water is not a good solvent in every situation. So you got to be careful of that, because not all problems will be water, and not all problems will the solvent be water. So you want to make sure that when you do across a problem, that you really understand sort of what the solvent is, and in addition to understanding that what the solvent is, that you make sure that you look up on the table correctly for the solvent. The other really important thing that sometimes people sort of related to this and water is you will need temperatures. You'll need like freezing point temperatures. You'll need maybe boiling point temperatures and some other problems. Not this particular problem. But when we look at like the normal freezing point, normal boiling point, sometimes people always have in their head, 0 degrees Celsius for water and 100 degrees Celsius. These are specific for water. And what that means is, if we are not using water as our solvent, in addition to probably on that table, or you might have to find in another source, the other important thing that you would have to sort of figure out is, what is the normal freezing point in this situation for whatever solvent it may be. So I will say a lot of times the solvent is water, but it's not always going to be water. But sometimes people always have sort of water's information in their head. They always want to use water's information in these problems. And again, a lot of times you'll be okay because it will be water, but it won't always be water. So cautionary note that if the solvent is not water, that means that obviously these temperatures that you probably have in your head may not be the correct temperatures, because again, if it's a different substance, it might have a different freezing point temperature or boiling point temperature. Any questions on that? Third thing that people sometimes kind of screw up on is actually what the meaning of this is. And a lot of times people just plug and chug into this equation and they solve for delta T of F. And they go, cool, that's their freezing point temperature. And that is actually not the freezing point temperature. It's important to remember that this delta means it's actually the change in the freezing point temperature. And that means that we need to figure out, really what this equals to. And as we see here, the change in the freezing point temperature is equal to the temperature of the solvent. So the temperature where the solvent normally would freeze, 0 degrees if we're talking about water, minus the temperature where the actual solution that you're talking about will actually freeze. And it's important in this case, because it's a freezing point depression, that means that the solution will freeze at a lower freezing point, that you actually, when you sort of figure it out, you actually need to do the solvent minus the solution. This will get you the correct, I guess the way to put that, this will get you the correct way of either adding or subtracting. So if you don't do it this way, solvent minus solution in this particular case, you will end up, or you will probably find yourself kind of adding when you should be subtracting and subtracting when you should be adding. So it's really important in this situation when we talk about the actual change in freezing point temperature, that's the solvent minus solution. And in a lot of problems, what you'll actually be solving for is this part of it. What is that temperature where that solution freezes, which means you would be taking the solvent minus the change in the freezing point temperature. So a lot of times you'll be actually kind of solving this way, temperature where the solvent normally boils and the change in the freezing point temperature. So this little part of it where it may not seem like it's a big issue actually is a big issue. And this arrangement is really important because, again, it will help you avoid sort of the math problems of adding or subtracting in the wrong situation. Again, as we talked about, the reason that's all occurring is we got these particles, they get in the way of them coming together. The other sort of important sort of property of solutions that is affected by this process is, as we touched upon earlier, the boiling point. So the boiling point, we see boiling point elevation, which means that where the solvent normally boils, we will now see that guy actually start to boil at a higher temperature because of all the particles that are dissolved in there. And to my earlier picture where I drew the kind of the circles at the beginning, you know, again, it's just all those things in the way. So it takes a little bit longer, a little bit more energy as it's kind of weaving and going around all the other particles in there for it to sort of escape and to start to boil. So that requires a little bit more energy to be put in there. The result of that is we see that the temperature where it starts to boil really starts to increase. So the presence of a non-volatile solvent just basically means that the solvent itself, I'm sorry, non-volatile solute, that it means that the solute itself that's dissolved in there won't go into the gas phase. It just kind of sits there. It's not going to evaporate or anything like that. We do see that the boiling point is raised compared to this pure solvent. You know, that's sort of the idea of antifreeze when we put it in our car. Antifreeze actually does both things. It's a freezing point depression and it's a boiling point elevation. That way, when you live in a really cold environment, when you have antifreeze in your car, it takes a little longer for that water to freeze, a much lower temperature for your water to freeze in your car, so it doesn't actually freeze everything that's in there. And vice versa, boiling point elevation, as things start to heat up. And if you live in a really hot temperature, you don't overboil. Again, it creates the boiling point of water to be much higher so things don't go crazy and boil over in sort of the summertime. We see pretty much an identical sort of formula here for our boiling point. That is the change in the boiling point temperature. So much like the other one was the freezing point temperature, this is our change in boiling point temp. KB, just like KF, is actually the boiling point constant. And our M here, again, is our molality, which is our moles per kilogram of solvent. Same sort of situation. Obviously, our molality is calculated the same way. Boiling point constant is really a table value in most cases. And just like with the freezing point one, it also is based on the solvent. So it is based on the solvent as well. So just as we talked about before, you know, if you are looking at water as your solvent, then obviously boiling point would be 100 degrees Celsius. But again, if it's not water, you would also need obviously the accompanying boiling point temperature that goes with it. Yeah, so your question is kind of these B's here, if you will. Yeah, these B's, just like the sort of F's that we saw in the previous one here, that's exactly what they mean. So when we see the delta TF or KF, or in this case, we're talking about the delta TB or the KB, it does refer to basically freezing point for the first one, and then this one would indicate that we're talking about boiling point here. That's basically what those B's basically represent. Other questions on that? Okay, so we got our boiling point temperature based on our solvent. We got our molality. Now, again, just like the previous one, when sometimes people use these equations, again, this first guy gets confused sometimes. People solve for it and think it's actually the boiling point of the actual solution. And again, it is not. It is the boiling point or the change in the boiling point temperature. It's basically, you know, how much the boiling point went up. So it went up by 3 degrees, it would be 3. If it went up by 5, it would be 5, and so forth. So we have sort of an important sort of meaning for our boiling point, our change in boiling point temperature. And this is actually the temperature of the solution minus the temperature of the solvent. Now, in this case, the boiling point is going to be going up, which means the solution would boil at a higher temperature than the solvent will. And in this case, we actually want to go solution minus the temperature where the solvent normally boils. And this will give us our proper sort of boiling point temperature. Now, this is opposite of what we did in the freezing. In the freezing, we did solvent minus solution. In the boiling, we did solution minus solvent. Again, this is an important sort of thing to make sure that you get the proper sort of sign, if you will, the proper adding or subtracting. In this case, again, in most problems, you most likely will be solving for the temperature of the solution, which means if we do that, the temperature of the solution would actually be the change in the boiling point temperature plus the temperature of the solvent. So again, that's an important relationship to make sure that in this case you sort of add rather than subtract, because it's a very common process where our problem where people will, you know, if we talk about sort of the change in boiling point being 5 degrees, for example, people will actually subtract it rather than add it. So instead of it boiling at 100 degrees, it boils at 95 degrees. And again, that's not elevation if it starts to boil at 95 degrees, right? Where we really want it to go from 100 to 105, right? And that's boiling point elevation. So as weird as it may sound, almost just as important as the formula, the calculation, is understanding, you know, these sort of differences here, what the change in that temperature basically represents. Any questions on that one there? Now, this is a table, not the one from your book, but you have a similar table. And this is a table where you can find those things like our KF value here and our KB value. Obviously, F, as we talked about, based on freezing point, and B based on boiling point. The units here are degrees Celsius divided by molality for like our KF or our KB. So let's talk about a couple of things about these units. First off, this is one place where I know we went through gases and all those type of things where we always talked about we need to take the temperature to Kelvin, you take temperature to Kelvin. This is one point where you can kind of leave the temperature in degrees Celsius, because most of the tables and stuff like that that you would find these values on, and as you can see, the constant has it in degrees Celsius. So this is one case where you actually probably don't want to convert to Kelvin, otherwise you'll be off by units. The other thing, obviously, this is molality here as well. But these are some different sort of solvents. And again, you can see that when you look on this list, for example, you don't find anything like a sodium chloride solution, a calcium chloride solution, or anything like that. A solution with glucose in it, glucose solution, nothing of those things. This is all based on the solvent. And again, in most cases, water is a lot of times what you use, which again would correspond to 0 degrees Celsius for the freezing point, a KF constant of 1.86, and 100 degrees Celsius for boiling point, and a KB constant of 0.512. Now, if our solvent wasn't water, which could happen if you were dealing with something perhaps that was nonpolar, maybe we would use something like carbon tetrachloride. And carbon tetrachloride, which is nonpolar, you can first off see that it has a much different freezing point than water. So why it's important to make sure that you get the appropriate freezing point. Also has a different boiling point than water. So again, if you're doing boiling point, important that you get the correct boiling point temperature. And also, as you can see, different values for the KF and the KB value. Same thing with benzene, different temperatures where they freeze and where they boil, and also different values for KF and KB. So again, sometimes a lot of examples will be water. Water will not always be the solvent, so you got to make sure that you grab sort of the right information as you do a problem like this. Any questions on that there? Yeah, if you need a table like this, it would be provided for you. Yeah, definitely. You don't have to go memorize the freezing point or boiling points of every solvent known to man, so it would definitely be provided for you. Along with obviously the KF values and the KB values and everything that you would find here as well. The only one that may not be provided for you, obviously, is water. You should hopefully know that the boiling point of water, the freezing point of water, is 100 degrees and 0 degrees. So that information may not be provided for you because that's something that's, I don't want to say common knowledge, but that's something that you probably should be aware of. But obviously, I wouldn't expect you to know the freezing point because I don't even know it either, to be honest with you, of, chloroform or the boiling point of it or something like that. But water, you definitely should know 0 degrees is the normal freezing point and 100 degrees Celsius is the normal boiling point. Other questions on that? All right. All right, so why don't you take a second here, see what you come up with and see what you come up with a problem like this. So what is the freezing point temperature, just so we're clear what you're looking for here? What is the freezing point temperature in degrees Celsius of a 1.7 molal ethylene glycol solution, an aqueous ethylene glycol solution? So take a second here and see what you come up with. All right, let's take a look at sort of what's going on here in this particular one. To answer your question, no, in most cases, so the question was, would you need to kind of convert the temperature into Fahrenheit? I would say yes, if they specifically ask you to do that. In most cases, they don't. In most cases, you'll be asked just what is the temperature, and usually degrees Celsius is usually actually okay to leave the temperature in. Again, obviously, if they sort of specifically sort of asked you, give the temperature in Fahrenheit or even give the temperature in Kelvin or some type of unit like that, then obviously you would want to do that. But with pretty much in these problems, without the sort of absence of any direction in terms of units on the temperature value, because the constant has degrees Celsius, you typically leave the final answer in degrees Celsius is usually what you would kind of go with. Other questions on that? Okay, so here we're looking at the freezing point. So obviously out of our two sort of formulas that relate to this sort of topics, we had one that dealt with freezing point and obviously one that dealt with boiling point. And our freezing point one is our basically delta TF is equal to KF times M. Now, a couple of these things, again, remember that in this case, we're talking about freezing point depression. Which means that our freezing point is going to be lower than where our solvent will be, which means, as we talked about, that this really means the change in the freezing point temperature is our solvent minus the temperature of our solution. The KF is a value that we would need to look up, and you may be going, well, again, this is what I was talking about before. People will look at this, go ethylene glycol. They'll come over here and go, I don't see ethylene glycol anywhere here. And again, remember that it is the solvent that you'll find on this table and not the solution. So again, we see something as aqueous. And again, unless otherwise specified, I think I'll spit that out. If you see aqueous, that's pretty much going to kind of indicate that water is the solvent, again, unless it specifically mentions something else there. So we would want to go to the table, obviously, and look at water. And here we're dealing with freezing points. So again, this is one that you should know, that water normally freezes at 0 degrees Celsius. And more importantly, for our calculations, our KF value here would be 1.86, it looks like. So we will have a KF value that is 1.86 degrees Celsius divided by molality. So we have that. In this particular case, you did not need to calculate the molality. They actually gave you the molality. So we actually have that. So we really have everything we need to kind of stick it into this equation. And if we do that and sort of solve for it, we get our change in freezing point temperature would equal our KF, which we got from the table, times the molality, which they gave us. And again, if they did not give it to us, we may have to calculate the molality. Here's what I was talking about earlier in terms of units and sort of to the question that was just asked. When we do this, the molality cancels out. It does leave us in units of degrees Celsius, which again, unless otherwise specified, you know, that's sort of the unit you could leave temperature values in for these type of problems. 1.86 times 1.7 gives us a 3.162. 0.162 R. If we kind of clean it up maybe a little bit, we'll go with 3.2 degrees Celsius. Any questions so far on that calculation? Now, a lot of people would be tempted to go, cool, I'm done. I'm going to throw a box around it, a nice non-square box there, and move on to the next problem. And technically speaking, if you did that, you know, you would get perhaps one of these, because this is not the actual answer to the question. And again, sometimes people, when they do these problems, think it is the answer. So we really don't want to box that here. What that 3.2 represents is not really where the solution is going to freeze. It represents basically how many degrees that the temperature has gone down to freeze, because it's a depression, from where the solvent normally freezes. So again, this is actually the change in the freezing point temperature. And that is why earlier, and we talked about it as well, this relationship is really where we're going to be able to figure out where the temperature of the actual solution is going to freeze. And we could do that simply by rearranging this. And if we rearrange this, we can rearrange this by taking the temperature to the other side of the solution and bring the change in freezing point temperature to the opposite side, which would be subtracting it. And basically we will then get our change in our freezing point. So this is where the other piece of information comes into play. Our water normally freezes at, by itself, 0 degrees Celsius. So now when I do that and I put this in here, temperature of my solution would equal 0 degrees Celsius, which is our normal freezing point, minus our change in freezing point temperature, 3.2 degrees Celsius, means that this solution will freeze at minus 3.2 degrees Celsius. And as weird as it sounds, that is how we get the proper minus in there. So instead of freezing at 0 degrees Celsius, drop it down, freezes at minus 3.2 degrees Celsius. And that is actually the answer. Because 3.2 degrees, right, if you box that, is actually a higher temperature than 0 degrees Celsius. And you would be implying that the freezing point actually went up in that case. So the negative here is really important to imply that the freezing point actually went down to minus 3.2 degrees. Any questions on any of those sort of steps? So this is sort of the idea of freezing point depression. You know, for example, we were talking about rock salt earlier, you know, make your own ice cream, you know, in like a plastic bag. put a bunch of ice, some rock salt, you know, it gets really, really cold and it will kind of freeze. The one that's the solution, the one that's the solvent. So water is the solvent in this case. The solution is basically the name of the solution, which in this case is an ethylene glycol solution. So the solution is the guy that has that name, the ethylene glycol. Is basically the name of the solution. It's also the solute, basically, right? And it's the solute, but that is actually the solution. But the water is the solvent because it's aqueous. Other questions on that? So let's take a look at another one and maybe some other sort of calculations that we could kind of get, or information that we could kind of get when we do some type of freezing point calculation or boiling point calculation here. Let me see what we got going on here. So in this case, we want to calculate the molar mass of a compound if a solution of 12 grams is dissolved in 80 grams of, dissolved in, let's see here, 80 grams of water, and it freezes at minus 1.94 degrees Celsius. So there's a couple of things that we're going to be looking at here when we do this calculation. But first off, we are going to be looking for the molar mass. So this is something a little bit different. We're not looking for the freezing point temperature or anything like that. It's actually given to us. So first off, a reminder of what molar mass means. Molar mass here means grams per mole. So we're ultimately looking for grams per mole. So the first thing we want to think about is, do we have any of that information given to us? So the molar mass of a compound, if a solution of 12 grams is dissolved in 80 grams of water. So obviously water here is our solvent. It's the larger part. So we're looking for really the molar mass of that guy that's dissolved in that water. So we have 12 grams, and that actually is the top part here. So we actually do have the top part here. The 80 grams is not used because it's the water. So that again is the solvent. This is going to be really the solute, the stuff dissolved in there. So at this point, what we need to do is really figure out the moles. And the moles is going to come from really the freezing point information. So we're talking about this compound freezing, which again takes us to our freezing point temperature formula. So change in freezing point is our Kf times our molality in this particular case. Now, we do have a couple of things given to us. We do have the temperature at which this guy freezes. So that's the freezing point temperature, minus 1.94 degrees Celsius. We do have the Kf. We know that the solvent is water. So the Kf here is going to be the same one that we just saw on the previous page, which was 1.86 degrees Celsius per molality. Now, first off, though, when we look at this number here, is it this guy? And the answer is no, it is not. Again, the guy on the right is our change in freezing point temperature. This is actually the temperature where the solution freezes. So we do need to use our relationship here that our change in our freezing point temperature is the temperature of the solvent minus the temperature of the solution. Now, since the solvent is water, the temperature where this guy normally boils or freezes, sorry, not boils, is 0 degrees Celsius. So if we put our numbers in here, that would give us 0 degrees Celsius minus a minus 1.94 degrees Celsius, gives us a change in freezing point of 1.94 degrees Celsius. This is how we get rid of the negative. Otherwise, we're going to end up with like a negative molar mass and stuff like that. So again, these little things here with the signs, the adding, the subtracting, you do have to be careful as you're doing these problems. It's a very common mistake. People kind of miss these little things. Any questions on that? The 1.94 does represent now the change in the freezing point temperature. We obviously have our Kf value. That's going to allow us to solve for molality. Why would it be important to solve for molality? Well, molality is moles of our solute divided by kilograms of our solvent. We're looking for the moles, right, to finish our project here. So if we rearrange this and we solve for it, and we end up with the molality is the change in the freezing point temperature divided by the Kf. That gives us our 1.94 degrees Celsius divided by our 1.86 degrees Celsius molality. Degrees Celsius cancel, molality ends up back up on top there when you do that, and we end up with 1.94 divided by 1.86, 1.043, we'll call it. We'll go with that. Now we have the molality, which is basically 1.04 moles per kilogram of solvent. We don't want both of these. We want, again, just the moles part. So we need to get rid of our kilograms of solvent. We could do that because we know that we have used 80 grams of our solvent. So if I take my 80 grams of solvent and convert it into kilograms, 1,000 grams in a kilogram gives me 0.08 kilograms. And basically I multiply these guys together, 0.08 kilograms of my solvent, kilograms of solvent cancel, leaves me with 0.0834 moles, which is now the bottom part. Now I have both things that I need to figure out the molar mass. So the molar mass here would be the grams, which is 12 grams, divided by the moles. And we end up with 12 divided by that, like 144, we'll call it on the round. Go 144 grams per mole. So you can see here, we could use our freezing point sort of information to calculate the molar mass of a substance that was basically dissolved in the solution, basically the solute here. Question on that calculation or any parts of that? So there's a lot of sort of applications that you can use with these freezing point equations, and the boiling point equations work the same way. You could do it obviously to find where something freezes, where something boils. You could actually do it as we just seen here, or we could use it to figure out how many moles or grams of a solute that's in there. We could also figure out the molar mass of it as well. Any questions on that one? Okay, they agree with us. That's good. All right, so why don't you give one a try here? How many grams of ethylene glycol must be added to 1 kilogram of water to give a solution that boils at 105 degrees Celsius? So take a second here and give that one a go, and I'll give you a reminder. We are talking now about boiling. So think about boiling. Again, kind of works very much like freezing, and see what you come up with. Before, we are now kind of switching in this problem to boiling point. Again, not much of a difference, but there are a couple of things we do want to watch out for. So obviously our change in our boiling point temperature will equal our Kb times our molality, which again, pretty identical to the freezing point one, except again here that this is going to be a boiling point elevation, which means we're going to get a higher boiling point in the solution than we are in the actual solvent. So remember that what that means is that our change in our boiling point is actually the temperature of the solution in this case minus the temperature of the solvent where it normally boils. And the other important thing obviously is we're looking for a Kb value. So first off, we're taking, we want to know how many grams of ethylene glycol. This is a molecular compound, not ionic, right? Carbons, hydrogens, oxygens. So that's molecular. compound. Basically stays together when it goes for a swim. But that really is kind of our solute. And we're adding it to our water, which is our solvent. And remember, everything about KF, KB, all that revolves around our solvent. So the first thing that we might be able to know is that our solvent of water normally will boil here at 100 degrees Celsius. We also need a KB value. And again, we would need to go back to that table there. And again, for water now, we saw that again, it does here at 100 degrees Celsius. But we see that again, the KB value here obviously is different than the KF value. So we want to make sure that we use the proper sort of value there for our KB, which would be 0.512. So coming back to it there. There we go. I think I just said 0.512 degrees Celsius divided by molality. Okay, so if we think about sort of the things that we got going on here, we do have the KB. We do have the temperature of where the solution boils at 105 degrees Celsius, and that's what that number represents. So much like what we just saw in the previous example, that is actually not the change in the boiling point temperature. So you would not want to stick 105 into this formula, which is again a common mistake that people make. That is why we need to look at the relationship that we see here. And we see that if we take the temperature of the solvent to the other side equals the temperature of the solution minus the normal or the change in boiling point temperature. I think I hit the wrong numbers there. I didn't need to rearrange. Got a little ahead of myself. Sorry about that. We actually have everything on the right-hand side there, so just plug it in would be a good idea. So let's try that again. Change in the boiling point temperature is our temperature of the solution minus the temperature of the solvent. Again, we have both of those numbers. So that is the temperature of the solution. In this case, boils at 105 degrees Celsius. The normal boiling point of our solvent is 100 degrees Celsius. That gives us a 5 degrees Celsius as our change in boiling point temperature. And that is what we have here. Any questions on that? So again, it's really important to make sure you just don't roll with like, that's a temperature, I'm just going to throw it in. You got to make sure that you understand what that temperature represents. We could do that because now we could kind of solve for molality here. Molality would be our change in our boiling point temperature divided by our KB. And that would give us our 5 degrees Celsius divided by our 0.512 degrees Celsius molality. And that is going to get us, if we do that, 5 divided by 0.152, that gives us, we'll call it a 9.77 molality. And again, if we sort of break that out into what that means, it means that we have 9.77 moles of our solute, which is really this guy in this case, our C2H6O2, divided by a kilograms of our solvent, which is basically water in this case, right? So we want grams, so we really need to get to moles of this guy. And we could do that because they were nice enough to tell us that we have added it to 1 kilogram of water, which means if we take this and we times it by the 1 kilogram of water, kilograms of water will cancel, and that will tell us that we now have 9.77 moles of our C2H6O2. Any questions on that so far? So you can hopefully kind of see that we're using the boiling point information here to really get us back to molality. And the reason why we're going for molality, other than the fact that that's sort of all the information we could solve for at that point, is because, again, molality is moles of the solute divided by kilograms of solvent. And that's going to allow us to get to moles of the solute like we just did. And from moles of the solute, we could use the molar mass to get to grams. So now it's just a conversion factor at this point to go from moles to grams. We would need the molar mass of our solute, which is 2 carbons at 12.01 plus 6 hydrogens at 1.008 and 2 oxygens. Looks like at 2 times 16 gives us a 6207. And that looks like we end up with perhaps 606 grams of this guy here would need to be dissolved in the solution. Any questions on any of those steps? So you can see here in this particular case, we use the difference in this boiling point of this particular solution to figure out how much of that solute was originally dissolved in there, basically to get us to that difference of 5 degrees Celsius in terms of where it boils. Any questions on that there? Okay. All right, there. So again, basically what the, there's a couple of things boxed, but again, this is our answer here. And again, basically what that means is in this particular example, that if you dumped in 606 grams of this ethylene glycol into water, kind of mix it up and stuff like that, then took that solution to boil, it would not boil at 100 degrees Celsius where water would normally boil because of everything that's been dissolved in there. That solution will now have to get up to 105 degrees Celsius in order for it to actually start to boil. Again, the sort of the idea of your antifreeze there in your car. All right. Hopefully they agree with us. Yeah, perfect. All right, here. So why don't you take a second here and see what you come up with this one. Calculate the boiling point of a solution made by dissolving 1 gram of glycerin, the C3H8O3, in 54 grams of water. So what is the boiling point of that solution? And again, degrees Celsius is good. All right, so here again, a couple of key things, obviously, as we are reading through this boiling point. So obviously that takes us to our boiling point equation that we've been dealing with. It's made by dissolving 1 gram of glycerin. Again, this is going to be our solute. It is a molecular guide, carbons, hydrogens, oxygens, covalent bonding, all that kind of stuff, no ions. 54 grams of water. So in the larger part here, which would be our solvent. Since water is our solvent, that is where our Kb value would come from. And obviously it would be the same Kb value if we went to that table as we just used in the previous problem, 0.512 it was. In addition, since we're doing boiling and our solvent's water, we also know that the temperature of our solvent, where it normally boils, will be 100 degrees Celsius. And lastly, the important relationship, as we talked about, right, is that the change in the boiling point temperature in this case, because it's going to be an elevation, it's the temperature of the solution minus the temperature of the solvent in this case. All right, so let's think about a couple things here. We are looking for the actual boiling point temperature. So really want to start by solving for this guy. We have the Kb. In this particular case, they are not giving us the molality, but we do have enough information to calculate the molality. We have the grams of our solute, which we can then convert into moles, and we have the mass of our solvent, right? So our molality would be moles of solute, kilograms of solvent. So we'll start with the solute part. We know that we have 1 gram of C3H8O3. We need to convert that into moles. So we're going to divide by the molar mass. And the molar mass of this guy, if I could grab my calculator here, is 3 times the 12.01 for the carbons, plus 8 times 1.008 for the hydrogens, plus 3 times 16 there for the oxygens. Looks like 9209 is our molar mass. Again, from the periodic table is where that came from. Grams are going to cancel, and that will give us our moles of approximately 0.01086 moles. So that is the top part. We then need kilograms of solvent. We know that the mass of the solvent here, of our solvent, is 54 grams. So we can convert that into kilograms by taking 1,000 grams as a kilogram. And that's going to give us 0.0540 kilograms. So we can do that easy conversion there. That is the bottom part. So we now have our molality, which would be 0.01086 moles divided by our kilograms of solvent here. And if we do that, it looks like 0.201 moles per kilogram, our little m for molality. Any questions on that there? That is what we need here for our molality. So we now are ready to go and kind of just plug it into that equation. And if we do that, we get that the change in the boiling point temperature will be our Kb, which is our 0.512 from the table. Our molality that we just calculated, molalities will cancel. And we end up with, we'll call it 0.103 degrees Celsius. Again, an important reminder that this number is not the boiling point temperature of that solution. It is simply the change in the boiling point. So that is where we need to take into our relationship here, our relationship that we see here, to actually get where that solution will boil by solving for the temperature of the solution. So if we rearrange that, the temperature of the solution will actually equal the change in the boiling point temperature plus, by bringing the solvent to the other side, the temperature of the solvent. That means that we get 0.103 degrees Celsius plus, not subtracting, 100 degrees Celsius gives us a boiling point of 100.1 degrees Celsius, give or take there. So in this particular case, this solution will boil at a whopping 0.1 degrees higher than water would normally boil if you just put 1 gram of glycerin in there. Any questions on it or the calculation? So it's really important that obviously you know how to do these things. You do need to be able to solve for a variety of things, including obviously, as we've done, grams of solute that's in there, boiling point temperatures, freezing point temperatures, something like molar mass. Again, you could kind of see that there's a lot of different pieces of information that you could kind of sort of calculate using freezing point temperatures and boiling point temperatures. Any questions on that there? So another sort of property of solutions that we want to talk about is, hopefully they agree with us. They do, looks like, so that's good. Another one is what is osmotic pressure. And osmotic pressure is basically when a solution, for example, is separated from its pure solvent by a semi-permeable membrane, which basically means allows certain things to go through, certain things do not go through the little membrane. At some point, the flow will be restricted by what is referred to as osmotic pressure. And that's basically sort of the atmospheric pressure pushing back down on it. So if you take something like a tube, for example, and within this tube, kind of have two sides, and you have a nice membrane there. And let's just say on one side you have salt water. On the other side you have just pure water. So what ends up happening is through the process of what's known as osmosis, solution or solvent molecules will move from a lower concentration to a higher concentration. And in this case, if we have pure water, it has nothing dissolved in it. So something with salt water has something like sodium chloride or something like that dissolved there in it. It has a higher concentration. So the natural flow through osmosis would be the pure water will kind of go flowing this way in an attempt to kind of dilute down the other side. And it will continue to flow until it hits a pressure that's equal to basically atmospheric pressure pushing down on it. And that is basically what is the osmotic pressure here. And basically when it does, it prevents any more sort of water molecules from pushing to the other side. It kind of stops it. As we'll talk about reverse osmosis, as you push it the other way. But in this sort of process here, we get this osmotic pressure. And it will stop really that continual flow of, say, solvent molecules across that membrane because of the pressure difference. And what we end up getting is we can actually calculate the osmotic pressure. This is the pi, but it actually represents the osmotic pressure, which is a fancy way of saying P, basically. And as you could kind of maybe see in here, that's where I wrote the P there. That is really based off of the ideal gas law, PV equals nRT, right? And if I solve for P, P is equal to nRT divided by V, which is what we have here. So this is really just an ideal gas law. And as we alluded to last time, remember that when we talk about units in the ideal gas law, they are very specific. And the two units here, right? N is moles. L is liters, and moles over liters is molarity, which is where the M comes from here. And that's how this guy gets reduced down to the molarity times RT. So although it may look really different, it is really just the ideal gas law. And when you try to calculate the osmotic pressure, people like to use fancy symbols and stuff like that, but it's really the same ideal gas law that we use in the gas chapter, which a very important reminder of that is we need to be careful on units here, right? Again, pressure needs to be atmospheres, volume needs to be liters, temperature needs to be Kelvin in this case. R obviously is our gas constant. And obviously N should be moles. So we can actually calculate the osmotic pressure and do some other calculations involving that. Ultimately, although it has a sort of a different formula, it really is just the ideal gas law. And I guess we will do some of that stuff tomorrow. So we'll wrap up this chapter tomorrow.